Hmm. So last time, we talked about the fundamental particles, right?
जी
And we started the third topic of nuclear and particle physics, and that was mainly about the particle zoo. But before talking about the particle zoo, we talked about two important concepts. One of them is the creation of universe, right? One of them is the creation of universe, and the second one is the annihilation of matter, right? So we talked about one important thing, that whenever something was created, at the same time we had an antiparticle as well. And that antiparticle is supposed to combine with the particle in any nearby future that would lead to the annihilation of matter. Got it?
जी
But now we need to talk about all those particles which make up a zoo of particles in physics, right? So first of all, we've got the standard model. First of all, we have got some sort of a standard model. And whenever you're talking about some sort of a standard model, in standard model, historically talking about it, first of all, the concept of atom was given by Democritus, remember?
जी
And Democritus basically considered atom to be an indivisible particle. Democritus basically considered atom to be an indivisible particle. But right after some, 3,000 years, Rutherford and Bohr concluded one thing, that atoms are not really the indivisible particle. Rather than that, atom is made up of electron, proton, and neutrons, right? Atom is made up of electrons, protons, and neutrons. Electrons reside around the nucleus, and protons and neutrons make up a nucleus, right?
जी
And thirdly, the recent developments. When we talked about the recent developments, whenever we're talking about the recent developments, we mean that after the discovery of instruments like the LINAC, right, and the CERN, right? So after talking about the LINAC and CERN, we concluded one important thing, and that one important thing was not even the electrons, protons, or neutrons are the fundamental particles. Rather than that, protons and even neutrons are also made up of, are also divisible, right? Okay? They're
जी
also divisible. And how they're divisible? That protons and neutrons are made up of quarks. Got it?
जी
They are made up of quarks, and quarks make up different series of particles like baryons. We're going to talk about the baryons. We're going to talk about the leptons. We're going to talk about the hadrons as well, right?
जी
So this was the first class. Quarks make up different classes of particles. One of them is the baryon. The second one was lepton, and the third one was hadron. But up till now, we consider electron to be a fundamental particle, right? There's nothing to worry about an electron. Electron is still considered to be a fundamental particle. But electron also got some sort of pairs as well, right? They also got some sort of pairs as well. And those pairs are known as leptons, right? The lepton is a class of atoms having some other fundamental particles as well. So this is what standard model tells us about, right? So first of all, we just concluded one important thing, that first of all, quarks are the fundamental particles up till now. Okay? Quarks
जी
are the fundamental particles up till now, and leptons are the fundamental particles as well, right?
जी
So we have got the leptons and we've got the quarks, which are still considered to be the fundamental particles, and they make up different classes of particles like baryons, like leptons, like hadrons as well. Got it?
जी
So first of all, we need to talk about quarks, right? What are the quarks and how many quarks we have got? We need to know their charges. We need to know their symbols. We need to know their types as well. Okay. So in total, we've got 6 quarks. One of them is basically you've got the up, then you have got some sort of a down quark, then you have got a strange, then you have got the, the charm. Charm quark is also known as a beauty quark. Apart from that, we've got the top, and then we've got the bottom as well, right?
जी,
So we've got these 6 types of quarks, and they make up, they make up different sort of uh, classes of atoms. Now, after talking about their types, we need to know their charges as well. So remember that whenever you're talking about the quarks, they've got different charges. Like for example, whenever you're talking about up quark, it got a charge of +2/3, right?
जी,
Whenever you're talking about a down quark, it got a charge of -1/3. Whenever you're talking about the strange one, it got a charge of -1/3 as well. Whenever you're talking about the charm or a beauty quark, it got a charge of +2/3 as well. Whenever you're talking about the top quark, it got a charge of +2/3 as well. And the bottom one got a charge of -1/3. Got it? Ji?
yep,
Apart from that, you also need to know their symbols. Up is a quark that is represented by U. Down is represented by D. Strange is represented by S. Charm is represented by C. Bottom by small b. And top by small t. Got it? Ji? So you need to
जी,
know their symbols and charges. And these are the first fundamental particles that we need to be concerned about all the times. Okay. Ji?
जी,
Now, if you remember, the other class of fundamental particles we had were the leptons. Remember,
yep,
we had leptons as well. If you're going to talk about the family of the leptons, how can you identify leptons? Remember that leptons do not experience any strong nuclear force. The simple identity mark of a lepton is that they do not experience a strong nuclear force. Is that clear, Ji?
जी,
Right? So when you're talking about the leptons, we've got different ones. We've got even 6 leptons as well. The first one of them is an electron, right? And then we've got a pair of electron, which is also known as a neutral pair of electron, that is also known as electron neutrino. We've got electron neutrino. And thirdly, we've got something like muon. In the fourth place, we've got muon neutrino, right? We've got something like this as well. In the fifth place, we've got tau, and then we've got the tau neutrino as well, right?
yep,
So these are the members of the families of the leptons, right? But we also need to know about their charges, about their symbols as well. So remember that electron, as we all know, that the charge on an electron is -1. Whenever you're going to talk about a neutrino, remember that it would always be having a charge of 0. Then muon also got a -1 charge. Muon neutrino got a charge of 0 as well. Tau got a charge of -1, and tau neutrino got a charge of 0 as well, right?
जी,
Okay. Talking about their symbols, how you're going to represent them. So remember that electron can be represented by E minus. Electron neutrino can be represented by VE. Muon is represented by mu. Muon neutrino is represented by V mu. Tau is represented by a stylish T, and then VT, right? So that is how we're going to talk about their symbols and these thingies. Is that clear?
yep,
Right? And remember that these are the 6 particles, right? 6 leptons. At the same time, we have got 6 quarks as well. But there is also one important thing that is understood. For every quark, there is an anti-particle as well, which is known as anti-quark as well, right?
जी
Antiparticle gives you some sort of an anti-quark. Okay ji? And
जी
whenever you're talking about an anti-quark, and whenever you've got the first one that is up, what is going to be an antiparticle of up? That has to be anti-up, represented by U slash. For down, it has to be anti-down. For strange, it has to be anti-strange. For charm, it has to be anti-charm. For top, it has to be anti-top as well, right?
जी
Okay. So, sorry, this is top, this is B. But it has to be T hash or B hash as well, right? So this is how you're going to talk about the antiparticle. Did you get that?
yeah
In the similar fashion, we've got the antiparticles of electrons as well. Let's say, remember one thing. When I talk about an antiparticle, everything remains the same apart from the symbol and the charge. Now, for example, if I'm talking about an anti-up quark, anti-up quark would always be having a charge of -2/3, right? Anti-down quark would always be having a charge of +1/3, right? They've got the opposite charges. Anti-strange quark would always be having +1/3. Anti-charm quark would always be having -2/3. Top quark would always be having -2/3. Bottom quark would always be having +1/3. Did you get that?
yeah
Right? So antiparticles means they've got the same masses, but they've got the opposite charges. And whenever they're going to combine, they'll create photons. And the creation of photons is basically the annihilation of the particle. Got it? Ji?
जी
In the similar fashion, when you talk about these leptons also got antiparticles as well, right? For example, the antiparticle of electron is known as a positron, right? Antiparticle of an electron is known as a positron. Got it? Ji?
जी
Now, similarly, antiparticle of an electron neutrino is known as a positron neutrino. Okay, positron neutrino. Antiparticle of muon is anti-muon, right? Antiparticle of muon neutrino has to be anti-muon neutrino, right? They've got the same thing but the opposite charges. For the tau, it has to be anti-tau as well. For tau neutrino, it has to be anti-tau neutrino. They've got the same thingies for all of them, but the only thing that's going to change is going to be their charges. Got it? When you talk
जी
about the positron, it would have a +1 charge. Since the charge on a neutrino was zero, the charge on an anti-neutrino or anti-electron neutrino would always be zero. There's +1, 0, +1, and 0 as well, right? So that is how we need to talk about antiparticles whenever you're talking about them. Got it?
जी
Okay. So now we've got the different class of particles. We've got to know that there are fundamental particles like leptons and quarks. Now we need to talk about that how quarks can lead to the formation of different classes of particles, right? And the first class of classes of particles, and the first class of particles we've got is a baryon. जी असद baryon क्या होता है? Have you ever heard about it?
जी
Whenever you talk about a baryon is basically a class of atom that is made up of 3 quarks.
जी
Got it? Ji?
yes
Okay. So whenever you're talking about the baryon, if 3 quarks are combined together, if 3 quarks are combined together, the resulting particle is baryon. Got it? Ji? The resulting
जी
particle is going to be a baryon. Did you get that?
yep
For example, whenever you're talking about a proton, remember that is a baryon. Even a neutron is a baryon as well, right? And the composition of proton, very important, remember that. that the composition of a proton would always be up, up, down. Okay.
जी.
And the composition of neutron would always be up, down, down. Did you get that?
Yeah.
And it has to be, the sum of the charges of up, up, and down should lead to the charge of a proton. If you remember, the charge of a proton was +1, right?
जी.
Charge on the up quark is something like 2 by 3, right? So 2 by 3 plus 2 by 3, and the charge on a down quark was -1 by 3. So when you're going to add them up, 2 plus 2, 4, 4 minus 1 going to be 3, 3 upon 3 going to be 1. So you can see that we're still having 1 as a final charge. Is that clear?
Yeah.
Up, down, down. So 2 by 3 minus 1 by 3 minus 1 by 3 going to get you 0. So you can see that neutron had no charge, so they're still giving you a 0 charge as well, right?
Yeah.
So apart from the protons and baryons, we've also got some other baryons as well. For example, in the third scenario, we've got a lambda 0 as well, right? Lambda 0 is a baryon as well. And the composition of a lambda baryon is up, down, strange, right?
Yeah.
In the similar fashion, since we've got protons, so this is, evident that we must be having an anti-proton as well. An anti-proton, whenever you're going to talk about it, anti-proton would always be having the same quarks, but they're antiparticles. Yani anti-up, anti-up, anti-down. Okay?
Yeah.
So that is how baryons are created, right? Now, the second class of particle that we're going to talk about is the mesons, right? We've got the mesons as well. So whenever you're going to talk about the mesons, so remember that mesons are composed of a quark and an anti-quark, okay? Whenever they're combined together, the resulting particle is a meson, right? So whenever a quark and an anti-quark combine together, they create mesons, right? So did you understand the composition of a meson?
जी.
Now there are some other, some other examples of mesons as well. For example, we've got a meson, a very important meson that is known as a pion. And secondly, we've got a kaon as well, right? So whenever you're going to talk about a pion, remember that pion is always made up of up and an anti-down quark, right? Did you get that?
जी.
And when you talk about the pion, pion is made up of up and anti-down. And whenever you're going to talk about a kaon is made up of a down and an anti-strange quark, right?
जी.
Thirdly, we've got another example of a meson, and that could be, this was a pion. We also got a pion positive as well. Pion positive. This is also a meson. The composition of a pion positive is going to be up and an anti-up. Do you understand?
जी.
So these are the mesons that we need to talk about. Okay.
Yeah.
Now, thirdly, we've got another class of particles, right? And that another class of particle are known as hadrons. Okay, Ji? So we have got some sort of hadrons as well. Remember that whenever you're talking about the quarks and whenever you're talking about whenever you're talking about the hadrons, remember that quarks or whatever other thingies we're talking about, like quarks in the case of a baryon or a meson, right? Quarks made up a baryon and a meson, right?
Yeah.
Remember that they interact via strong nuclear force. So they interact via strong nuclear force. And both of them can be considered in a single class of particles that is known as a hadron. Got it? Ji?
Mhm.
And then you have got a particle, right? Any particle, remember that. I'm just going to define a hadron now. Remember that any particle which experiences, any particle that experiences the strong force, any particle that experiences a strong force is called a hadron. Got it? Ji? Any
Mhm.
particle that can experience a strong nuclear force is known as a hadron. So remember that both baryons or mesons are hadrons as well, right? But lepton,
Mhm.
remember that, do not experience strong nuclear force. So that is why it is in a separate class of particle from the hadrons, right? When you talk when you talk about the meson, when you talk about the hadrons, right? They are they, they are some sort of hadrons. But remember that leptons are not hadrons. Got it? Leptons would
Ji.
never be the hadrons. Is that clear?
Yeah.
Okay. Now, apart from that, the last thing that you need to talk about, we have got the particle reactions. Whenever these particles interact with one another, remember that they need to conserve a few important laws, right? We have got some sort of particle reactions, right? And whenever you're talking about the particle reactions, for example, if there is any alpha decay happening or a beta decay happening or a beta minus decay happening, for example, let me take a few examples. If you're talking about a particle reaction, for example, you've got U235 and 92. It is going to create a thorium, which is at 231 and 90 plus an alpha particle 4 and 2, right? Don't you think charges and masses are conserved on both the sides of this equation,
Yes.
right? Charges and are conserved on both the sides of this equation. Is that clear?
Yeah.
But now you need to remember one more important thing, that whenever such reactions of particles are happening, there are four conservation laws that you need to check. What are those four conservation laws? First of all, there must be the conservation of charge. So there is some sort of charge conservation. Secondly, there must be some sort of a mass conservation, right? Thirdly, whenever you're going to talk about it, there must be a conservation of a baryon number on both the sides, right? So this
Ji.
is the conservation of baryon number, right? And
Mhm.
fourthly, you must be having some sort of conservation of lepton number. Is that clear?
Yeah.
So we've got the charge conservation to talk about. We've got the mass conservation to talk about. We've got the conservation of a baryon number. We've got the conservation of lepton number whenever we are talking about it, right?
Ji.
Okay. Getting back to the class of leptons that we had, first of all, to talk about, I'm pretty sure, the masses conservation can be checked out by like this, right? The
Yeah.
charge conservation can be checked out by like this. You can see that 235 is equal to 221 plus 4. It means that mass is conserved on both the sides, right? If you talk about the conservation of the charge, you can see that 92 is equal to 90 plus 2. So the charge conservation is fulfilled as well. Got it?
Yeah.
Okay. But now uh, there are many other numbers. You don't know what is the lepton number of a baryon. What is a lepton what is a lepton number of a uranium here as well, right? So we need to talk about the lepton number of the fundamental particles as well, right?
Ji.
Okay, so first of all, talking about the leptons. Talking about these leptons, we had electrons, electron neutrinos, muons, muon neutrinos, tau, tau neutrino. we need to know their lepton numbers as well, right? So I'm making another table, and that's going to get me their lepton number, right? So remember that the lepton number of all the leptons would always be 1, 1, 1, 1, 1, 1, and 1, right? And the
Yeah.
lepton number of all the antiparticles would be -1, right? Lepton number for all the positrons would always be -1, -1, -1, -1, -1, -1. Since they are the fundamental particles, so you're going to talk about their baryon number. Remember that the baryon number of both the leptons and anti-leptons would always be 0, right? So there is one more important property of lepton, that lepton would always be having a baryon number of 0. Does that make some sense?
Yeah.
Right? Ji? Okay.
Yeah.
Now we also need to talk about some other particles as well, which are very important. Like, for example, we're going to talk about the proton. We're going to talk about the neutron. We're going to talk about some other, like a neutral pion. We're going to talk about in the fourth place, like something like we've got the neutron pion. Apart from that, we've got the pi plus as well, right? Then we have
Yeah.
got the down quark as well, right? And then we have got the Z minus as well, right? So these are some important particles whose lepton numbers and the baryon numbers we need to know, right? We need to cram them, right? So if you're talking about the lepton number of all these protons, neutrons, natural pion, pi plus, down quark, and Z minus, they would all have a lepton number of 0, right?
Yeah.
They would all have a lepton number of 0, right? That is how you're going to talk about the lepton number. But apart from the lepton number, we've got the next important thing, and that is going to be the baryon number, right? Jay? And whenever you're talking about the baryon number, remember that proton would always be having a baryon number of +1. Similarly, +1 for the bis baryon number. Neutral pion would always be having 0, 0. And then you've got the down quark, it must always be +1/3. And the Z minus would always be +1. Got it? Ji? These are the baryon numbers. Would you remember that?
Yeah.
Okay. Now, at the end of the day, let's talk about an example which is conserving all these laws, right? So an example which is conserving all these laws is some sort of a beta minus decay, right? We've got some sort of a beta minus decay. So in a beta minus decay, what does really happen? I'm just giving you an example, and that is a beta minus decay. So in beta minus decay, what does really happen? In beta minus decay, you've got an up quark, and you've got a down quark, and down quark decays into an up quark plus a beta. It would get you a beta, and plus an anti-electron neutrino, right? That would get you 0 and 0. Got it? Ji?
Yeah.
So if this reaction can happen, we need to understand a few important things, that if the charge is conserved, right? Apart from the charge, is the baryon number being conserved? Is the lepton number being conserved? So talking about the charge, first of all, what is the charge on the down quark?
-1/3.
And what is the charge on an up quark?
+2/3.
And what is the charge on a beta quark? What is the charge on a beta particle or an electron?
-1.
-1. And a charge on an anti-particle of a neutrino, anti-electron neutrino, has to be 0. So now, can you see that both the sides are equal or not? Yes, they are. You've got
Yeah.
-1/3, 2/3, -1, right?
G.
So you can see that both the sides are equal. Now, talking about the baryon number, what is the baryon number on a down quark? What is the baryon number of the down quark?
Um,
+1/3, remember that.
yeah. जी.
The baryon number of an up quark plus 1 by 3 as well. Beta would get 0 and 0. So you can see that baryon number is conserved as well, right?
जी.
Lepton number, the lepton number of a down quark is 0. Lepton number of an up quark is 0. Beta is plus 1, right? And the anti-neutrino would have a negative 1. So you can see that even this side is conserved as well, right?
जी.
So for this reaction to happen, their charge is conserved, their baryon number is conserved, their lepton number is conserved. So what does that mean? That this reaction can happen because it is fulfilling all the laws of conservation. Is that clear?
Yeah.
Right?
जी.
So that is what we needed to talk about, right? We're done with the whole chapter of nuclear and particle physics. ठीक है जी?